Let's look at an example of that application of the squeeze theorem, and that was to prove that the limit as sine of x over x is equal to 1. We can't directly substitute 0 in because we get an indeterminate form. So what we'll do is we'll draw a reference angle here, so we're going to draw a unit circle-ish. Maybe it just looks a little bit like an oval, but we'll pretend it's the circle. And we have length 1 and 1 to the edges of the circle. We're going to drop down a perpendicular for the height, and that's going to be sine of that angle. So we'll go ahead and call that angle x. I think the book uses theta, it's just a variable. And we're going to go ahead and find the area of this red triangle, and that's just going to be 1, which is the base, times sine of x, and we're going to divide that by 2. So just sine x over 2. And then we're going to look at the area of this sector. So if you remember your area of the sector formula, this one's going to be, because it's of unit length, unit radius, it's just going to be x over 2 is the area of that sector. And what we're going to end up doing is we're going to compare those two areas. So you can see that the red triangle is certainly inside the blue sector. So the red triangle is going to have a smaller area than the blue sector. And then we're going to draw out the tangent. So the tangent, and I'm also going to make my unit circle a little bit better so it looks more like a tangent. So this is what the tangent is. We extend this triangle out with this orange line right here and connects this tangent line, so we're going to define the tangent to be the length of that line segment from the x-axis up to the point of intersection between those two orange lines. So it'll be tangent of that angle, and area of that is going to be tan over 2. And what we'll do is we'll go ahead and compare those three areas. So we're going smallest to largest. So sine x over 2 is the smallest, then the area of the sector is next smallest, and then the tangent of x over 2 is the largest. So for now what we'll do is we'll just assume that the x is positive, so we don't have to worry about whether the sign is negative or positive. We're in quadrant 1. We're going to go ahead and multiply both sides by 2 over sine x. So the sine over x times 2 over sine x, that's going to be 1. When we multiply the x over 2 times the 2 over sine x, that's going to give us x over sine x. And then the last one, tan, is sine over cosine. So the 2's are going to cancel, the sines are going to cancel, and we'll have the cosine left over in the denominator. Again, since x is positive, these are all positive. Of course, they're greater than 1 also. So if I have like 1 is less than 3, which is less than 5, if I take the reciprocals, the 5 will change into a 1/5, and that'll be the smallest. The 3 will change into the 1/3, and that'll be in the middle, and the reciprocal of 1 is just 1. So this is going to reverse the order. So when we take those reciprocals, we're going to have the reciprocal of cosine, or 1 over cosine, which is cosine, reciprocal of x over sine x, which is the sine x over x, and then reciprocal of 1 is 1. And so as cosine goes to 0, or as the x goes to 0, cosine is going to go to 1. The constant 1 as we go to 0 is just going to be 1. And the sine of x over x is actually going to be sandwiched in between the cosine x and the 1. So it doesn't have anywhere else to go. So it's going to have to be squeezed in there. Now, if we went on the other side, because we know I said x is positive, but the limit we should be going for both directions. If x were negative, cosine is an even function, so the cosine of x is the same thing as cosine of minus x. Sine is an odd function, so sine of negative x would be negative sine x. So this particular piece here would be okay because the negatives would end up dividing out, because the sine of negative x is negative sine, and then you'd have a negative x in the denominator, so our inequality would be preserved.